Hello everyone. In this video, we'll explore k-means clustering and how we can automate the process of determining the optimal number of clusters in our data. So what is k-means? It's an unsupervised learning algorithm that groups data into a chosen number of clusters called k. Here's how it works. First, we place k centroids, our initial guesses. Then, each point is assigned to its nearest centroid forming clusters. Next, every centroid moves to the mean of its group. We repeat these two steps, assign, then update, and the centroids gradually settle into place. After a few iterations, the clusters stop changing and the algorithm converges. So why choose k-means? Because it scales. Hierarchical clustering compares every pair of the points and its cost grows with the square of your data. K-means grows almost linearly. That means it handles large datasets, stays memory light, no giant distance metrics, and converges in just a handful of iterations. But there's a catch. K-means needs you to choose K upfront, and the wrong K gives you the wrong clusters. One common approach is the elbow method. We plot the error for each value of K and look for the elbow, where adding clusters stops helping. The K here equals 3. The problem? Reading that elbow is manual and often subjective. A human has to eyeball it. So what if the machine could decide for us? We can automate it. Run k-means across many values of k, score each, and detect the elbow automatically. The optimal number of clusters chosen for you. We'll build exactly that in Python next. To the practical side of the things, we'll be performing the automation of the k-means clustering in this code. To do that, I'll be using a very famous dataset called the Iris dataset, which is available in sklearn. So first, what I will be doing is I'll be loading that dataset and doing some exploration on it. So let me run this code. Now what you see over here is this dataset has 4 independent variables with one dependent variable. So it has this sepal length, sepal width, petal length, petal width. And based on these 4, it is classified into one of these classes. So there are a total of 3 distinct classes, Setosa, versicolor, and virginica. So this is the input data set that will be clustered. Now, just to remind everyone, while performing the process of clustering, we will be letting go of this class variable here because it's an unsupervised clustering. So instead of using this class, we'll just use these 4 variables over here and perform the clustering basis these 4. So moving to the next point, we need to do some pre-processing before we can do the clustering. So for k-means, it's required that we do a standard scaling of the data. So we try to move the mean of the data to 0 and standard deviation of 1. And we do it through standard scaler. We do a fit transform. And we are also doing a PCA on top of the same standardized data because we would want to also plot these clusters later. And we'll be doing that by using the first 2 principal components on this data. So let me run this one. Now in the next point, in the next code block, this is where we try to create the optimal number of clusters in a regular k-means clustering problem. This is what is called as the elbow curve method. So if I run this, what it does is it starts with a number of cluster options starting from 1 or 2 and goes all the way up to the total number of data points. Generally, we don't go that far, but I think in this one we have just 150 records. So for this demonstration, I am going till all those points. What we do here is we continue for each iteration, we continue to define a k-means object, this classifier, and we fit it to the existing data frame, and then we record the inertia, or what is called as the within cluster sum of squares, and we keep appending it by each point, and then the resulting curve, what we get is what is called as an elbow curve. Now, if we have to use this elbow curve manually to determine the optimal number of clusters, we would have to use the human intuition or the judgment to find out an elbow which looks somewhere like here. So it looks to be somewhere around 10, but from the above point over here, it ideally should have only 3 classes. So that is where we may have an error in judgment when a human goes in and tries to find the optimal clusters. So what we do here is we automate the process, and the entire automation is done in this block. What we are doing here is, for each point on this graph, we are first trying to determine the slope. So as you can see, starting number of clusters, the slope is quite high. All the slope is on the negative side because it's going downwards. So here the slope would be pretty drastic, and here the slope would be pretty close to 0 because it's almost flatlining here. But this is the area which is the interesting part. So even this area would have some slope, and this point would have like a -1 kind of slope. And what is required to be done is, first we perform the change in the slope. So first we calculate the slope of the within cluster sum of squares over here in this construct. And in the second construct, which is also called list comprehension, we perform the change in change of slope. So it's like delta 2 within cluster sum of squares, because we want to see at which point the slope changes the fastest, because that is the point which we are looking for. So we do this in the second step, and then we assign the optimal number of clusters to the point which gives the highest value of the change with this argmax argument here. And then we add a 2 because we are shifting the curve by 2 when we are doing a 2 times derivative. And we also add a 1 because in Python, the indexing starts with 0. So a 0 cluster would be typically a one cluster. A cluster with an index 0 would be cluster 1. So we add 2 and 1, so we add 3. Now if I run this, it says the optimal number of clusters from elbow curve is 3. So this 3 is coming in line with these 3 categories. Just to do a sanity check. So now, since the machine has automatically created an optimal number of clusters, and if you remember, with human intuition, we were thinking it would be somewhere around here in 10, but the graphics over here could be misleading. So the absolute number says it's 3, and which also makes sense because we have 3 different classes here. So coming to the actual clustering part, we will take this 3 and put in the n clusters and perform the clustering. So as you can see, at least in the head top 5 records, wherever the class is Setosa, it is putting it as cluster ID 1. And we'll explore the other classes as well as we go along the code. In the next part, we will be using the PCA done in the previous part to visualize how these clusters look. So we are using the PC principal component 1 and 2 to basically see how well the clusters are formed, at least on a visual basis. So we do see like 3 distinct clusters. The cluster 0 is the blue cluster green is cluster 2, and the orange one is cluster 1. So they're pretty separated out, with the exception of this cluster 1 and cluster 0 and cluster 2, which are very close to each other. So the next part, we are just trying to see how do these three clusters and the already provided class, which is the dependent variable here, uh, correlate with each other. So as you can see, the cluster one is purely setosa. For versicolor, it is divided 78% between cluster 0 and 22 between cluster 2. And for virginica, it's the opposite. So 28% cluster 0 and 72% in cluster 2. So this is not a perfect clustering which is happening over here, but the objective of this demonstration was not to do like a perfect clustering, but more to show the viewers how we can go ahead and perform this automation of the elbow curve method over here, which we have done. Thanks for watching this video. I hope you enjoyed watching it. If you found this video helpful and learned something new, then please like and share this video and subscribe to my channel. See you in the next video.